So, yeah, go ahead.
Well, I was just going to say I was doing a little bit of exploration around LORA, following on from last week's conversation, and happened to, I think Jeff has spent time watching videos from Andreas, and he was talking about a particular project that used this Meshtastic, which can't confirm exactly that these are the exact right boards, but as Jeff mentioned, he had the Adafruit module was somewhat limited because of all the things that they had added to the board, and he somewhat limited on the number of pins, and I didn't have time yet to look at how many actual pins would be available on this, but that's just a little bit of research that I had done. Again, thinking through, I really like Jeff's design where he has on his radio control, or his, I'll call it control station, whether it's manual or whether it's ROS driven, and part of the way he does that is has a microcontroller on the rover to be that single point of interface. Anyway, enough blathering on for me. That's a little bit of research that I've done. That's the only progress that I've made. I'm going to rebuild my electronics board with, I think, Arduino every boards, just to get around the over-the-air programming, but that's where my head is at. Anyway, that's it. You wanted to comment on that, Jeff?
So the only progress I made was I finally stuck a Teensy 3.2 and one of those Adafruit radio boards that's just the radio and there's no extra parts on the board, as opposed to the little this is the little board from Adafruit that just has it's a radio, but it also has a voltage regulator and some level translation on it. So theoretically, you could connect this to a 5-volt in any 5-volt processor in addition to run it on a 3.3-volt processor. And the board like this has no level translation, so you have to hook it up to a 3.3-volt processor, which the Teensy is a 3.3-volt processor, so that works. So what I wanted to mention was my almost all of my experience and all the digging I've done is from the Adafruit website. And let me pull up something here. Let me pull up a new Adafruit website. Adafruit, go there, maximize that. So on the Adafruit website, if you just search for RFM, and I searched for RFM 95, and I'll in a second here I'll talk about what the difference of that is. So here's that little board right here that I was just talking about. So if we pull that up and look at it, see it's the board. Looks like it's just a better picture of what we were looking at. And here, let me back up and back up. Oh, stop it. Their website's a little too cute. Adafruit.
Well, somebody who has fruit in their name, you got to think that they're.
Yeah, maybe. So anyway, I'm just going to post that to chat if I can figure out how to do this here now. Where did my chat stuff go? Yeah, let me stop screen sharing so I can get stuff back. So chat. So just so people can follow along, that's just the basic link to Adafruit. And if you just type in Adafruit, it'll suggest adafruit.com. So that's not a big deal. So anyway, go back to screen share it again. So on their website, actually we could. Now let's start with where I was. So you go up here, we type in RFM 95. And it turns out there is the concept of an RFM 95 and there's a concept of RFM 69. And I don't know what the complete difference is. So if we scroll down here, I think it'll still bring up the 69 ones. But the ones that are RFM 69 are about, the radios are half the price. Here's one that's 69. And this is one that's just simply the radio on the board. So it's just like the board I've got here, but it's got the other, but it's got the other module on it. So it's got the RFM 69 module. And I think it's the fact that 95 is either is more of a packet radio or has extra software in it or something. I'm not sure what the difference is. But when I bought mine, I bought the RFM 95. And it's, as I say, it's the more expensive. It costs about twice as much. See right here, it's $10 for the for just the bare board. And if we look at the very top one, come on. La 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 la. Well, it's also confusing on here because even though we're looking at this one right here, it says $34.95. The price is actually at the bottom down here. So the one for the RFM 95 board, like I've got, that's just the chip on the board, and you're supposed to plug it on top of a Feather adapter and then plug it in, or you can plug it in any of their Feather radio or Feather microprocessors that they make, because that's just their trademark. So they make various processors that have that particular pinout on there. And I
But that
bought
900 megahertz is $20.
yes. Now you can, as I said, you can. Let me verify that I actually had that right. It wasn't confusing me. So here's the RFM 69 on the same format, and it's $10. So it's half the price for this radio. And I didn't dig into why there's a difference there, but it seemed like the RFM 95 seemed to be the one that would, send packets back and forth easily. And it could be the 69 will work too. It could be the 69 is more of one. Let's see if I can get some information on it here. That might be like a serial port replacement. So you just hook it up to the serial port at one end and shove data into it. At the other end, hook it up to the serial port, you get your data back. That might be the difference between the two. And if we look at this here, short hop, blah. It does say packetized. And so I guess you'd have to dig through to figure out what the difference is between these. But I know the RFM 95 ones do work for for what I'm doing. Now the other thing is you can either buy them in the 433 megahertz range, or you can buy them in the 900 megahertz range. And so there's the difference. You got RFM 69, RFM 95, and then you got 433 megahertz or 900 megahertz. That's your four options when you go to buy these things. Now, I believe technically, if you're in Europe, you're supposed to run 433 megahertz. If the United States, you're supposed to run 900 megahertz. And they'll let you buy either one, and people buy them and use them, and they're probably not going to come after you unless you're causing enough interference with your neighbors or somebody, and then they're going to say, we don't like what you're doing, and they'll tell you to stop doing it. I'm guessing is what's going to happen on that. And then they've got these, so on the Adafruit website, then they have these hookup. Put this back down so I can see where I'm at. They got these hookup guides, and they might go through and tell you, or let's go to the top here and just type in LORA, and it's going to show us radios. Oh, come on, settle down. Okay. So it shows you, I think, let's look at, tell us there's a checkbox that says show me the best match recently added. Maybe learn is what I want. And they've got various tutorials here on how to get things to work too. And what's this one doing? Raspberry Pi, weather monitoring. And then So I talked about the 4 different options for the radio itself, and then the way they package it. We'll go into that in a second here, because as I scroll through, I think, oh, here they're telling me things that would be good, also be good to know. So when you go to pick these things, you have to figure out all the different pieces. And this one, well, it says on a Raspberry Pi, but it shows various boards. So anyway, if you dig through here on their tutorials, they'll give you more information on all this stuff. And essentially what I just wanted a device that I could connect up just like an Arduino and connect it up to joysticks and switches and so forth, and just read the data and send it to my vehicle. There it receives it and then does whatever I want to do with it at that point. And once it gets the far end, you could just use, send the data out the USB port of, if you're using a Teensy, send it out the USB port, either onto your Linux box, or that, I guess that's typically what you would do at that point. Or the Teensy's got UARTs built into it. So if you wanted to have the receiver Teensy talk to your low-level microcontroller, you could connect that directly that way. I chose to use a CAN bus simply because I was trying to copy an industrial remote control system they were using. So that's why I went with CAN bus. But basically, I just received the data as a packet of numbers, and then I can either write on the Teensy, I can parse those out to do something, or I could just send the whole block of numbers. In my case, I send it over to my low-level microcontroller, and then it parses the incoming data and says, oh, this is joystick 1, joystick 2, and so forth. And here's some digital bits that came across. So it decides what to do with all that stuff. And then the other thing I have a physical relay, one of those little relay modules that's got some drivers, so you can connect it right to logic. So I've got one of the outputs on the Teensy is driving that relay. So if everybody is happy all the way along, it'll turn that relay on, and that enables my main drive motors. And then if I have any problems, because on my box I got this e-stop switch in the middle here, and that's connected. If you get to the back of it, I don't know if you can see it or not, but back in here, there's the switch, and it's just simply the wires from that are connected to the processor board, and it just knows whether the switch is on or off. So basically, if the e-stop switch is enabled on the remote, and as long as the battery on the remote is working, as long as the thing is turned on, there's various things here. Well, if I am within range, then basically I put all that data into my packet, send it to the receiver on the robot, and if it's happy with everything that it sees, then it says, okay, let's turn on that e-stop relay, so I get power to the motors at that point.
And how many amperes does that relay support?
It's just one of those you find everywhere on eBay or Amazon. It's probably like a 1 amp or 3 amp relay. But what I do is, I don't have one handy, but it's just those little boards. They're about this big. It's got a relay and some pins on it. But what I do, that's one of the things in my circuit that gives me permission to turn on the motors. So that in my on the rest of the circuit on the robot, I've got the e-stop switch, which is physically on the back of the robot here, which I don't have any way to zoom in on that, but there's another one of those switches right there. So I essentially have power coming from the battery to that first physical e-stop switch, and then that is in series with the relay from the remote control system. And there might be one. So it's those two in series, the relay and the physical switch. And then those drive, I've got an automotive relay for the back motor and an automotive relay for the giant servo in the front on my steering. I think those are rated at 40 amps. And just by looking around, you can get the relays in the same package that are anywhere from like 10 amps up to like 70 amps or something, I think, just by picking and choosing which relays you want. So the little relay is just simply there to convert my logic signal from my radio into a switch closure that goes into the rest of my e-stop series circuit. And then actually on the far end of those two, the coil on those two automotive relays, that goes to a MOSFET that can be controlled from the low-level microcontroller. So it gets a vote too if it wants to. I haven't figured out anything to do with that yet, but So right now, when my low-level microcontroller powers up, it just says, write these two I/O pins to a high, and that enables the whole, both e-stop circuits for my two motors. And if I wanted to, something in the software could say, well, something doesn't look right, or we're about to hit something, it could just drop those two pins and also kill power to the motors if I wanted to do that. So now
The heavy power is going through the automotive relays. The smaller relay is just engaging the automotive relay.
yes. So the small switch is in series with the e-stop switch on the back of the thing. So it's just it's probably maybe 100 milliamps going through that whole circuit, but it's just a way you can get multiple things to control it. So if I wanted to, I could put another e-stop switch on the front and put that in series also. So you turn off any switch, it will shut the thing down. And on mine, I don't have it kill everything. I just have it kill the main power to the motors. I know one guy on the Homebrew Robotics said that, his opinion on an e-stop, you want to use it if the thing catches fire or it's breaking things, then he wants to hit his e-stop and have it kill everything. But I like to have it just simply make the thing come to a stop, and then you can go out and your computers are still running, so you don't lose all the information of why did it die in the first place, and that's always very handy to know. So yeah, you have to weigh that to decide how you want to do that. You could even add a switch that's a pause switch, and then have another one that's your e-stop switch. And in fact, on mine, I could do that. I've got this switch up here. It's just a 2-position toggle switch, and in the down position, I'm treating that as the manual mode. And now at that point, my joysticks are active, so I can move these around, and the vehicle will move. And also I'm using that signal it's connected to my flashing beacon. So in the down position, the beacon flashes orange as long as the e-stop is not active. And if I flip the switch up like that, now my robot ignores these joysticks, so they won't do anything. It's now accepting commands from ROS. So if ROS is putting out command velocity messages, it'll say, oh, I should use those to control the speed and the steering. And then also like the switch here in the up position, now my beacon flashes blue for the blue flashing, saying it's an autonomous mode. And anytime if I push the e-stop switch, it's supposed to come to a stop, and then the beacon will flash red. And that's really just a combination of taking the various bits from the switches I'm creating on the box, and in the low-level microcontroller deciding what do I want to do with those. So the low-level microcontroller just says, oh, this switch is on, this switch is off. The joysticks are putting out this numerical value. The e-stop switch is putting out these bits, and it's just up to it's up to you to decide what you want to do with that information.
And that firmware is all running on the microcontroller in your control box.
Correct. The teensy on the remote control receiver just simply receives the packets and sends a text message over to that microcontroller. Oh, it also has that e-stop relay connected to it. So the e-stop is somewhat separated from everything else, although I do know once I send the text message over the low-level microcontroller, it can also see the bits that's controlling that e-stop relay, so it knows what's going on. And if I wanted to, I could then feed that back into ROS if I had a reason to do that. Eventually you need to come up with something that says, oh, somebody hit an e-stop, you need to tell ROS, shut down and stop trying to do what you're trying to do. So if it's trying to drive around doing some autonomous thing, and you can treat that one of two ways. Either say, hit the e-stop, the vehicle will come to a stop, and ROS just keeps waiting. ROS is now in a pause mode. The only problem with that is if you're running the standard navigation stacks that they give you, they also have recovery behaviors built in. So if it's trying to get from point A to point B and something's in the way of it, or it pauses for some reason, it's going to say, oh, we're making no progress. Here, let me try to do a rotational clearing. It's got all these different things that it'll try to do. Now, you can probably just go in and turn those off. If you go into the configuration file, you can probably say, don't do rotational clearing, and don't try to back up and clear it. It just simply, if you're telling it to go forward, it won't. Just tell Ross to just sit and be patient and wait for it. And that way you could use your e-stop switch as just a pause button. Now on mine, since I've got that switch that switches between autonomous mode and manual mode, if I put it back in manual mode, that will effectively pause my robot, even though Ross is saying drive forward, drive forward, drive forward. It'll simply ignore that. And when I turn the switch back to autonomous mode, it'll take off from where it was. And that would also give you the option, you can put it in manual mode and reposition it, drive around with the joystick and reposition it, and then give it back to Ross, and Ross will start moving and say, "Oh, that's not where I thought it was," and it'll correct for it and try to work. I haven't played with that enough to know how useful that's actually going to be, but so I just went down the whole path of, how I get from my remote control box out to my vehicle. It runs the e-stop circuit, and then otherwise all the extra information just goes to the low-level microcontroller to make it drive, i.e. control the steering, control the forward, backward speed, and all these extra switches. I can make them do lots of, if I got enough switches, I can assign them to anything I want. It's just whatever I can dream up is how that part works. So any direct questions on it, or should go back to the Adafruit stuff?
If I look at, just sharing my screen again. And I know your configuration is, highly customized, and how many pins do I need? I mean, effectively, this is an ESP32 with LORA capability.
Right.
I don't know how many pins are available on this for.
Yeah, go to click that and then put your cursor over so it'll zoom in on that.
I mean, it doesn't really.
Sometimes they'll give you a little chart, like in the upper left-hand corner there, they give you a little chart. Did any of those say radio pins?
Hold on a second.
So one of the first things you have to do, you have to look at this board and say, are all these pins available to be used?
Which no doubt they're not.
Well, maybe they are. It depends how many pins are on the processor to start with. If you got way too many pins, then
Oh, well, wait a second. Here's a little, you see this red arrow?
yeah,
I think they're saying those are taken.
yeah, it says they must not be used for other purpose. So yeah, so right offhand, you can cross those off and say, I do not have those available. And then the next thing, you might want to look at how many analog inputs do you have. And I know like these boards I have seem to have way too many analog inputs, but something like a,
I see
what's this thing?
ADC.
Well, okay, on the chart on the left says green ones. Green ones are the analogs. So you do have various ones available there. Yeah, that's a good picture now. We can see everything. So that's the next thing. You decide, do I want one joystick or two joysticks? Do I want to put some pots on the remote control box? Because you could just put, a physical pot that you turn it, or you could get a linear pot. So you got a slide pot. Any one of those will take an analog input or require an analog input. So if you're considering this board, it might be best if you just print out this picture and then go through and cross off the ones that say they're used for the radio or used for the OLED. Just cross those pins off so they're not taking up room. And then just say, okay, the next thing is analog inputs. So you say how many joysticks, how many pots do I have? And say, well, we seem to have a bunch of analog input pins here that are not connected to the radio. So that's good. And then things left over, say switches and push buttons, then whatever leftover digital pins you have could be connected to those. Now,
Yeah, there appears to be, well, when it says GPIO, that I don't want to move my mouse because it's a good picture. see the greens, and to the left of the greens, you see purples that has like GPIO 32.
Yes. Now,
33.
the way you read this is you've got a physical IO pin on the board. You can see, see where it's soldered there in this picture. And then they got a little black line or a little black dot with a line running out. So that first column on either side, that's what they call the analog digital pins. So in your analog or in your Arduino code, you'd say, I want to turn on pin. Let's grab a random one here. Well, here's another interesting thing I just noticed. If you look at the pin 32, so on the right, just to the right of that display, it says pin 32, then it says crystal 32. Now it could be there's a 32 kHz crystal on the board that if you try to use this as a digital pin, you may be able to do that, but then your 32 megahertz oscillator will not run. And that may or may not be a problem. Typically, that 32 megahertz oscillator is used for a real-time clock on the board. If you're trying to keep track of the time, that runs an internal real-time clock peripheral inside of it. It probably has like an 8 megahertz crystal to actually run the processor. So that may or may not be an issue to use those pins that say crystal 32. So anyway, it says analog, or it says Arduino digital pin 32, or that can be the crystal 32, what's your 32 kHz crystal, or it can be a GPIO 32, and that it seems to have an asterisk by it, and I don't see anything telling you what that means, but maybe all of those. Well, some of them have asterisks and some don't. And then so going across to the right, or it could be used for an analog input, or it could be used as a touch pin, apparently. And if you haven't played with the touch pins, you basically take that, you run a piece of wire out to like a flat spot on a printed circuit board, or a piece of aluminum foil glued down. You put your finger on it, and it, without being a physical switch, you can touch that, and it works. A lot of new consumer stuff that comes out works that way. So you got the touch pads on there, and just simply
capacitive inductance or something like that.
Yeah, it's probably capacitive is what they use. So if you wanted to, you could do the touch inputs. Now I'm going to recommend you don't on something, any industrial vehicle, don't put stuff on like that, because that's just going to it's going to pick up noise, and you're going to accidentally put your hand on it, and it's going to think, oh, I should drive forward at 100 miles an hour. So I would recommend you either use physical push buttons or physical switches on this stuff. So anyway, that's how you read this chart. If there's a physical pin on the chip, and then you've got the two inside columns are the Arduino, what they call the Arduino digital pins. I think if you look on your chart over on the left, it calls those physical pins in that little chart in the upper left-hand corner. So again, it comes back to the fact you just have to look at this chart, and as I said, if you want analog inputs, make sure you got enough of those, because whatever's left over can now become digital pins for digital inputs or digital outputs. And another thing to note here, you go down on the right to the thing that's got the little hump in there. It says Arduino pin 25, GPIO 25, ADC 8. So it can be used in analog. It can also be used as a DAC. So you can generate a voltage coming off that without doing anything fancy. I think it'll put out a real voltage. And then it says LED. So that's on a typical Arduino board, they usually have that pin 13 LED. Well, that's what they're telling you here, is that pin is connected to the LED on your printed circuit board right here. And what I did on mine, I just ran a wire from there out to a resistor and an LED on my front panel. So this one right here showing up, that red LED right there is actually the LED pin on my Teensy. It's just running in parallel with it. So even though it's being used for something on the board, well, you can go ahead and use it. You could just use it for any digital I/O pin. It's just that then on your board, wherever your LED on the board is, it's going to flash every time, or it's going to follow whatever you tell it to do. So you could use that if you're going to bring it out your panel like I did. That's real handy because it's already defined as an LED, and you can just go ahead and hook that up. Anything else of note? And then if you look on the that DAC, I noticed in the chart in the upper left-hand corner, it's got the squiggly line says that's a DAC. Now, a lot of times on the chart, it'll say these can be used as PWM pins. So that's That's what I expected that to be, but it's not. It's for the DAC pins. So the thing we just went over, the pin with the LED has a DAC, and the pin down below, the next one down has it has a DAC, but the next one down also is connected to radio. So you can't use that pin anyway because that's part of the radio stuff. So first of all, eliminate all the radio pins. Then look at it, see how many analog pins you're going to need, and assign those. And whatever's left over, you can use for your digital inputs and outputs. Now, one more thing to keep in mind. So the board that Bob bought has a display on it, and this board has a display on it. Since this LORA is bidirectional communication, you can set it up where it says the remote will read its joysticks and push buttons and send that information across to the robot, and then it sends back an acknowledge. So you should always you send out, say, here's the data, and wait for the acknowledge to come back. You either get, say, it was good, or you got a timeout. Well, you can also, you can send a packet of data at that point. So if you wanted to, you could send back your heading, your speed, your status you're in, and put it right on your display you've got here. So you could just see it, as long as that display is visible on your remote control. And I think Bob said he put a piece of plexiglass over the top of his stuff. He even put I think he put a hinged door so he can see the thing, and he had some push buttons on it. And this has a couple of push buttons. One I think says program and one says reset. So typically you're not going to be using those push buttons anyway. So, but if you cut a hole in your box so you can see through it and put a piece of plexiglass over it, then you should be able to see this display. I don't know how visible it would be out in the sunlight, so that may or may not be the answer. And besides this display, if you send back just status bits, you can now put a bunch of LEDs on your remote control box, so you can turn those individually on and off with whatever IO pins you have left over here. And if you get really strapped, you can get the like I2C IO expanders, so you can generate more IO pins by just using the 2 I2C pins on here, or you can get shift registers, both parallel input and parallel output shift registers, and that takes like 3 bits to run one of those. So if you wanted to, you can put an 8-bit shift register, or let's say an output. So you put an 8-bit output shift register, and it takes 3 bits to shift the data out. And if you need more, then you put another one in series. Now you got 16 bits. You just keep stacking them up. So you could get 64 or 128 output bits if you want to do that, all from 3 IO pins that are on your board. And then if you want to do inputs, you can use the other type of shift register that inputs 8 bits at a time. And again, it takes like 3 wires to hook it up, and you can stack them up, have 8 bits, 16 bits, 24 bits, 32 bits, whatever you want. So you can, if you're really strapped, you could do that. That would be another way to get around it. And I could do that on mine too right now. I keep whining the amount of pins. Well, if I just give up a couple of the switches and hook up shift registers or the I2C IO expanders, you know, I could generate a lot of IO if I really wanted to. It's just that it's nice if just right on the board that you buy, you get enough places to hook everything up to it. Did they mention if this has more IO pins on the back of the board, the way that Teensy's do? Maybe zoom out to the previous page and see if they show anything there.
Trying to get there. That's not the one.
So just hover over on the left there. Just hover over those and see if it shows the back of the board. That is the back, and it doesn't look like it has extra IO pins there. So they do bring them all out like you would hope they would. Now, another thing to look at on something like this, look at the pin spacing and see if that'll plug into a proto board, or if you have to go to, you know, you can always go to just a perf board like this that's got, you know, random holes everywhere. So if you can find something that tells you what the spacing is there, you know, it may not plug into a board like this because it just simply, it might be too wide to fit. So that's just one more thing to think about. So one comment on this it looks like it probably has enough IO to do most things you want. And it's got the display on there. So if you wanted to send data back, you could send data back from the robot and display it on there, whatever data you want. You send it across, you decide how to display it and how to interpret that. Another thing you can do is you can make menus. So you can put a little menu on this thing. So I say, you can put some push buttons on your box and say, you got like an up, down, and a left, right push button, and then like an enter push button. So that'd take a total of 5 buttons if you want to do it that way. And you could say, on your main menu, you say, I want to say, what is my task that I want to run? And the next one might be run a circle test, and there might be run a square test. There might be calibrate GPS, whatever you want them to be. And then basically, so you select the menu option you want there and then hit your enter button, and I can bring up, say, another level of menu. Then under that, you'd have, say, under the run a task, you can say, well, mow the hayfield, mow the front yard, go get the mail, whatever you want. So you can just stack it up. And so it's just up to you to define, what you want that menu stuff to be. So that's two different things. You can either display data from the robot, or you could have your own menu. And then once you select the right menu, when you say enter, then it would send that over the robot and go out and try to mow the hayfield or whatever you want it to do. So it seems like for a remote control transmitter, this might be a good solution, because it seems to have, at first glance, it looks like it has enough IO, but you have to check that. It's got that display on there, which is also advantageous for making menus or displaying. You'd have to look at that display. If it's a full graphics display, you might even be able to put, waveforms on there as you watch the thing ramp up to speed and ramp back down. You might, use it like a little oscilloscope. It doesn't look like it's real high resolution, but you can get various things on there. So there's a lot of things there that might be beneficial for trying to build the remote side of a remote control system. So then in a second, we can contrast this to what Bob bought. And another comment, you obviously don't have to have the same type of processor at both ends, because mine, I've got the, look, how do I keep losing those? It's right here in front of me. Here it is. But I've got the Adafruit board that has the Cortex M0 processor on it, and then our radio. So this is a fully contained board like this ESP32 board you're looking at. You just put power on this, and it'll power up and run. You just put the code in, and it'll do remote control. And then on the other end, I've got I basically have these parts on the other end right now inside my robot. So I've got one of the Adafruit boards that's just the radio on a board, and then down here. It's really annoying this is backwards. So down here, I got the Teensy 3.2. So there's a different processor than what's on the transmit side. But the radio, since the radio, they're both, I bought them both from Adafruit, and I don't know that they are, the same brand of radio, but I know that they work together. If Adafruit says buy this, it works. I figured that was good enough for me. The other point was, So in my case, since I have, I just have the low-level microcontroller. I don't have, in Bob's case, he bought a board that plugs into a Raspberry Pi. Now, the board for the Raspberry Pi, it has a radio and it's got a little OLED display. So it's essentially like this ESP32 board here. And you plug it into the Raspberry Pi and load their sample code. And he apparently, he got it running far enough that when he powers it up, his little OLED says RFM 95 detected, which is good, because otherwise it'll say RFM 95 not detected, and that means your wiring is screwed up or your code that you specified is not working. So he got it far enough to see that is talking. Now, one problem you might have to consider if you're plugging this into a Raspberry Pi, that means now you've got code running under Linux that is talking to that radio. And I think when I went and looked at it, they were using Circuit Python. They're not using C or some other thing. So you have to get their code, which is running in what they want you to run in, which is Circuit Python. And now keep in mind, that is now running on top of Linux. So you have a full Linux install there. So you're getting somewhat away from direct access from your remote to your vehicle. You're getting, you start putting Raspberry Pis in between there. Well, I don't know how stable the Linux on Raspberry Pi is these days. I don't know how much you can trust it. And then once you put something on top of that, like say CircuitPython, I don't know how well that's tested and all these other things. So you're getting further away from the fact where you've just got a single board where you're talking directly to the radio and controlling IO pins. That to me seems like a lot safer than trying to run everything through a Raspberry Pi and a full operating system. Because if it decides to go get flaky, let's say you do it this way. You got the board plugged into a Raspberry Pi. You take one of the GPIO pins on your Raspberry Pi and hook it to an e-stop relay. Well, how much are you guaranteed that if you hit the e-stop switch on your remote, that going all the way through the radio and the CircuitPython and Linux and everything else on a Raspberry Pi, are you guaranteed that that relay pin is going to follow the way you want it to? Now, if you get a lower system where you don't have a full operating system, say you're running on an Arduino board or a Teensy board, or in this case, an ESP32 board, you don't have, the ESP32 has an RTOS built into it. And an RTOS is a small operating system. It's basically a dispatcher. It lets you write individual programs, and then this thing will, it passes out and says, here, run this program, run this program, run this program. And it's meant to make it easier to program, and you get faster control on everything. So if you're doing, machine control, it's sometimes good to have an RTOS in there. But
your low-level steering controller, as an example, running just, where is when you're adjusting your steering and it says, hey, I need to steer a little bit more to the left to get to the goal, or I need to steer a little bit more right to get to the goal, where is that processing going on?
On your actual vehicle where you're trying to run your power steering motor, you've got a Teensy. I assume you're using a Teensy 3.2 to do that.
No, I'm not asking about mine. I'm asking about yours.
On mine, I basically avoided that because I put a giant RC servo on there. So I just put out a pulse width modulation that says turn to 10 degrees or turn to 20 degrees, and the RC servo does that. So essentially, when I get data coming in from the remote, I've got a number from the joystick that says plus or minus whatever the number is. We could say plus or minus 100%. And then it's up to me to scale that number into a value that the RC servo understands. So it's just a conversion that goes on between there. And in your case, you have a number either coming in from a ROS message, or you could have a number coming in from your remote control. It's just a matter of you deciding which one do you want to honor. And as I say on mine, I've got that switch. I've got this switch right here that it's either in manual mode or ROS mode. And so in my low-level microcontroller, I just say, oh, it's in manual mode. So I will take the data coming from the joysticks and scale that and pass it to your Teensy 3.2 doing your steering control. Or if the switch is in the other position, it says, oh, I will take any incoming command velocity messages and take that number and scale it and pass that to the Teensy 3.2 on the steering controller. So again, it's just a matter of you have to decide how you want this stuff to work. And essentially on mine, I just have a software multiplexer in my low-level controller that says either accept data from the remote control joysticks, or accept it from the command velocity coming in from ROS. And that again was just what I decided to do. There's lots of different things you could do there. So let's see, I went down the path saying, well, Bob's going to run his on a Raspberry Pi. You may or may not be guaranteed that if you're trying to run an e-stop relay that's going to operate for you. So the other thing I was thinking about, if you have any relay that you're trying to control, I need to go search on eBay and Amazon and see if somebody already makes it. I'd like to find a relay. You have to continually give it pulses. And as long as you keep pulsing it, the relay will engage and stay engaged. And if you stop pulsing the thing, then it will disengage. So for some reason, it's connected to, on mine right now, it's connected to a Teensy 3.2, or in Bob's case, it's going to be connected to Raspberry Pi. If the code gets lost and forgets what it's doing, it's probably going to stop pulsing that pin. It's either going to leave it high or leave it low. But if it requires you have to pulse it, that's one more safety feature. So it gets around the fact that if the thing just locks up on you, you don't want to leave your e-stop relay on and have no way to turn the thing off. And even better solution would be if you had to put out either a code, or the timing of your pulses has to be within a certain range for the thing to honor what you're doing.
Right.
Actually, I think probably in the radio control industry, you can probably get a relay that's meant to plug into an RC servo, and it's expecting it to be within a certain range for the relay to turn on. That might be a quick solution right there. So on your whatever your microcontroller is, you just generate an RC type pulse of whatever position they want you to be in, and that would probably be safer than just wiring the thing up. And the bottom line is, you can hook up and make this stuff work. There's various levels you can do to this, and some may be more safe than others, but you could start with a simple thing. You had that key fob and a relay, and that does indeed work, but you run into problems if you're out of range or your battery's dead or you've got interference or whatever. It's going to ignore you when you need it most, and that's what it comes down to. You always, every time you go to drive it, if you're going to use that kind of system, every time you go to drive it, you should test that first. Start the vehicle up and prove if you push your button, it's going to kill it, and that verifies your battery is good at that point. And then otherwise, as you drive around for half a day, you're hoping that when you hit that button, it will stop. So it's just a matter of there's more guesswork, and you're putting a lot of trust into that. And that's why using a radio that's so the next, I was going to say the next step up is to have codes on the thing, but I'm guessing that key fob you have is built like a garage door opener. So probably if you open it up, there's probably like 20 dip switches in there, and you set a code on that, for your particular garage door and or your particular vehicle. So that's more safe than if you just have, say, if you have a push button, that's these little $3 transmitter receiver pairs you can buy, and simply put a push button on it. And when you push the thing, it applies power. It's putting on a continuous, say 433 megahertz or 315 or 815, whatever the numbers are, it just puts out a continuous signal. And the receiver says, oh, I see that signal coming in. I will do something with the output. It's either going to give you a high or a low output. So that right there has no redundancy, no way to distinguish between anybody else's radios that's out there. So the next step up is if you have something that works like a garage door opener, so you push the button and it's got a code on the switches inside, and then your receiver has switches inside of it, and those codes have to match. So that's more secure than just blatantly putting out a burst of frequency at some frequency. So that's good because of that. But now if you go to a two-way communication, which the LORA radio has, and if you're doing it over Wi-Fi, you can have a two-way communication or Bluetooth. And if I forget, remind me to come back to the Wi-Fi and Bluetooth and the LoRa when I'm done with this, whatever I was talking about here. So if you got two-way communication, now you have a situation where you say, here's the data I want you to use, and you broadcast that out, and you wait for an acknowledged message to come back. And if you don't get the acknowledged message, well, that's a problem. Now on mine, I foolishly made my remote control the master. So it's just got a loop inside that says, go out and read the joysticks and switches, package that up into a message and broadcast that out. And then the next line says, wait for a response to come back, and it's got a timeout on that. So if it doesn't get the response back, it knows that message did not go through. And right now, since it's on the remote control, the only thing I could do is say, turn on an LED or something. It can't physically stop the vehicle because I picked the wrong end. Now, what I could do is I could swap those. I could make the robot the master. So it does its loop simply says, read up any data that I want to send and put on your display, like say take the heading and the velocity and whatever, and send that to the remote control. and it'll be just sitting there waiting for something to happen. When that comes in, you can put the stuff on the display and it says, oh, I just got a request for data. Now read up your joystick and your switches, build the message and send it back. So now the actual joysticks and switches becomes the acknowledgement. And so you send it back to the robot and say, okay, I got the response in a correct amount of time. Everybody's happy. If it times out, then you can activate the e-stop relay on the vehicle and make it come to a stop. So if the communication is not going correctly and you start losing packets, or somebody next door turns on something that, interferes with the radio, if you're not getting the correct data all the way through, so you send out, send me the data, it sends you the joystick data as an acknowledgement. If you don't get that acknowledgement, you just shut the thing down. So that's another reason to have the two-way communication on this stuff.
And you wanted to mention something about Wi-Fi or Bluetooth?
Yeah, the thing I was going to point out, this board right here, right in the description, I don't see it. Most of the time, an ESP32 will have Wi-Fi and Bluetooth built into the thing. So another option you could run multiple networks between your remote and your vehicle. So if you wanted to, you could run LORA, and you could run Wi-Fi, and you can run Bluetooth. And now when you send the message across, they all have to agree. So that makes it even more safe at that point. And I'm still making the assumption you're going to be standing fairly close to the vehicle with your remote control. That's not necessary. You don't have to do that, but I'm thinking if you are fairly close to it, that that any of these networks should actually work. Or in this case, you might want to run, say, the LoRa to do your e-stop and your switches and pots, whatever you got on it, and then use the Wi-Fi. You might want to send messages back and forth for your little display on there or something. So you could, if the board you buy happens to have more than one type of network on it, you could actually do that too. Just run parallel radios at the same time.
Yeah, I'm not seeing anybody reference.
You just scroll to the top and type in Wi-Fi for a search and see, or BLE might be a.
You want me to go up to this search bar?
Just do Control F to do a find. And that'll search on this page.
No, it does say Bluetooth with Wi-Fi.
This looks like it's still the same board. What is that picture up there? Oh, they got a keypad connected. I think they're showing the back of the board is what that picture was.
They have a video. That's what was up there.
And you and all the stuff. It's always good to go watch their videos and see what they say about it. Maybe give you some suggestions on different ways to do it or whatever.
But it does say Bluetooth and Wi-Fi. Be interesting though to see if all those chips are taken.
And I don't know if they use I don't know if those use the same antenna that the LoRa does. They might have a separate antenna connector on the board to make those work. I think if you do show a picture of the top of the board, I think there is a. Well, we'll see how many. See, the one coming off the right, I think, is with the LoRa. And well, maybe look at the back of the board. I don't see another connector there.
Well, there's a squiggly line there.
Yeah, that might be the antenna. So that may be a fairly short range. But as I say, back to my argument, don't do like Kyler does and have the tractor half a mile away and expect, make sure the network you're running will talk that far reliably. And my opinion is don't be in that position in the first place. Don't turn a giant vehicle loose like he does. But if he wants to do that, that's what he's going to do. So if you had this kind of
there's
thing,
the Wi-Fi antenna right there.
Oh, and it does have that squiggly line, so it could be that the squiggly line might be the Bluetooth antenna.
Well, I think they're doing a little shenanigans with the picture because on this picture,
That doesn't surprise me.
you don't have the
Oh,
little copper twisted
yeah,
deal. You just have the wire circuit.
yeah. And I'm assuming that the Wi-Fi and the Bluetooth are not going to take up any more I/O pins. I think that's just a function of the processor itself. So that's just something extra you would have. Or you'd have the option that your remote control box could be talking to your laptop that's right next to you, either with Bluetooth or Wi-Fi. You know, so you got lots of options.
Well, it's an interesting board.
This board is interesting, and the fact that we were looking at the stuff brings up, you know, it gave me a chance to say, you know, here's what I suggest, here's what I don't suggest. So if we go all the way back to the beginning, you know, I said there's RFM 95 and RFM 69 boards, and I don't know, I've never looked into what the difference is between those, so that might be something to track down and see what's going on. And the fact that, oh, as I say, the boards that Bob bought, let me go back to Adafruit. Let me try this again. And say, well, we'll just pull up this one. Maybe it'll give me a direct link here. And here's something interesting now. This one says RFM 96. So I don't know if 96, well, it says 433. So this I believe is the board that Bob bought, and this will plug directly into a Raspberry Pi. And he does have one of these boards plugged into a Raspberry Pi, and the screen comes up and says RFM 95 radio connected. So he's gotten that far with it. Now he also wants to take this board and put it onto build his remote control out of it. And basically, if you can get the pins coming off this thing, the thing I was going to mention to him, maybe he'll watch this video, but if they flip the board over on the back, so it turns out here's the 40 pin connector up here that plugs into a Raspberry Pi, and he took some header pins, like these kind of pins, and bent them so he could get, so the thing would plug into, he bent one out and one in, so it'll plug into his proto board. But also, if you look at the back of the board, these pins across here, maybe if we look at the front of the board, so they got these pins across here and they're all numbered. That essentially is the same pins going to your 40 pins up here. And you could probably get everything you need off that and not have to make that weird adapter that he made. And then in addition to that, let's see, can I zoom in on that? Well, no, I can't. So anyway, there's a group, I think 6 pins here, there's 5 pins here, and there's 5 pins here. So these 5 are the ones that talk to the radio. So there's, that says reset, chip select, clock, and D0 and D1. I think the D0 and D1 are for the OLED display. So he's got 3 options to connect to this. He can even plug wires or adapters into this 40 pin socket, or he's got this strip all the way across here that probably has all the pins on. I'd have to go look at the schematic to see, or they might list it. If you dig through here, they might tell you what those pins are. Or he's got these pins on the board down here. And one other thing to consider, I can't read that, but like off the radio, let's see, do you say I or Q? The interrupt request is actually one of the IO pins from the radio. So it's just a matter of, in order for him to get this to work, he just simply has to figure out which of the 6 wires does he need for the radio, which of the 2 wires does he need for the OLED display, and he has to hook up power and ground to the board. So he takes those signals and connects them up to say a Teensy 3.2. This board he has should work, and that way he'd have the same board at both ends. You always get the point where, well, what if you burn out a board? You don't know if it's bad or not. It's always good to have 2 of them, so that way he would have two of the same board that he could swap back and forth to test this stuff out. And if you go through, typically on Adafruit, you go down here and it says something about, here's the, they keep moving this around, so it's harder to find, but they say it's the primary guide for hooking these up. So if you go on that one, and it'll say pin out somewhere. And those pins I was just talking about. So here's those 2 blocks of pins that you could hook up individual wires to, or you could put pins in there. You don't want the pins sticking down because now it won't plug into your Raspberry Pi anymore. So don't solder pins sticking down, because you're going to find out real quick, oh, now it won't plug in anymore. You can have those pins sticking up. But like in his case, if he's going to put this in a box and put a plastic lid over it, well, now the plastic lid and the pins are going to be in the way. And then let's scroll down a little further. It looks like right here, it's got the little pads where you can cut the trace in between if you want to disconnect them for some reason. I'm not sure what that's for. So we'll scroll down some more. And it says there is the OLED. Here, he's got 3 push buttons on his board. It's not going to tell us. So maybe it's not going to tell us what this strip across here. But I think if you look at it hard enough, I think these pins across there, you can also wire to those individually. So he could just solder wires into these pins and run them over. Get the jumper wires that have the connectors on the end. So you could just say get a 12-inch one and cut it in half, and then say solder wires at this end, and then the other end has the jumper wires. I think everybody knows what I'm talking about when I say jumper wires, but there's got to be some land here. Oh, like these kind of wires. Here's a short one. This is probably called a 3-inch one, and it's female to female. And this one I think is a 12-inch one. That's female to female. So what you could do is you could cut that in half, and then get 2 wires, and then at the one end, at this end, you solder these 2 onto your board, and the other end you can plug these into your pins on your processor board. So that's another way to do that. So it's just a matter of figuring out, physically how do you connect all this stuff together. And part of it is just figuring out which pins to hook up to, and I think there's enough information for that you should be able to get that either figured out, or I could point him to. Last meeting I said here's the link for that page that I found, and I forgot to put it on, so I'll just post that right now. So I'll take that, and how do I get back to my chat again? Stop chat. I'll just post a link with no explanation. So this is the page we're looking at last time. If you dig down here far enough, the guy said he works on a Seed Studio board, but does not work on some other board. And finally, a guy went around and hooked the thing up. Can I do this? He wired up this right here is one of the little one of these boards. So he's got this. See, am I sharing? No, I'm not sharing.
Yes. Well, I saw the board.
Well, so then no, I'm not sharing. Let me go back. So in the description, or in that web page that I was pointed to, so finally at the bottom, a guy said, all right, I'll hook it up. He's got a Teensy 3.2, and he's got one of these little Adafruit boards connected to it. And it did a couple of things. It told me which SPI pins they're using, because if you pull up the Teensy chart, I think it's over here in this corner. It's got the primary and the alternate SPI. I didn't know which one they're using. I figured the ones that are in dark letters over here is the ones that will work. And after reading this with this web page, it turns out, yes, those are the ones you want. So it'd be the Arduino pins 11, 12, and 13 is the SPI. And if you connect to that, then the default code will use those. The only drawback is the pin 13, which again, I don't know. Here we do this. So the pin 13 over here is also, how do you make these cameras focus? Anyway, that says LED 0. So that's the LED on the board. So now when your SPI runs, every time it sends a packet, your LED is going to flicker, and you can't use that LED for anything else because it's part of your radio circuit now. Then the other thing is, if you go look at the sample code, it'll say you use like pins 8, 9, and 10 or something for your chip select and IRQ and all that stuff. And so it tells you which ones to connect. So this guy showed it actually hooked together. And bottom line was that the guy said when he had it hooked to a Seed Studio board, he didn't have to hook up the IRQ and the reset pin But when he hooks up the Teensy, it turns out you do have to hook those up. And I can't imagine why it works on the Seed Studio board without hooking those up. The bottom line is hook up all 6 wires that they tell you to, and the sample code from, let's see, am I sharing? No, I'm not sharing. If you use the sample code from the Teensy stuff, I think if you want to run it on a Teensy 3.2, you simply go out to go to your Arduino IDE and say manage libraries, and say I want to add in the Teensy. I don't know if it just says Teensy or you have specifically say Teensy 3.2, and I think it adds in everything that Teensy has. So once you get that, you go over to examples on the Teensy or on the Arduino IDE and scroll down where it says Teensy, and under that scroll down to where it says LORA transmit example and LORA receive example, and those you click on those and they will come up and you're ready to go. You don't have to go screw around and go find libraries somewhere else. I think that will bring up what you need, although you may have to also install the radio library itself. But I think there's descriptions out there on how to do that. So once you get into the Teensy code, it says uncomment the block of code below for the board that you have. So you go down the line, you say, one says Teensy 3.2, you uncomment that. It says chip select will be on this pin. It says reset will be on this pin, IRQ will be on this pin. So use those pins and wire them up, and it should indeed work. So to sum up here, you can use various processors to do this. You could probably use various radios. If I go look on just on eBay or Amazon and look up a radio, look up a LORA radio 915 megahertz, there's various ones out there you can buy. I don't know if they're cheaper or not, but people seem to have them working. You go look on YouTube and they get them wired up and you're running. So I don't know. I still have this question. I don't know if I can take an RFM 95 board from Adafruit and say buy something from SparkFun, and if the two will talk to each other. I think it's a fundamental thing about that. Then they say, well, the RFM 95 uses there's a part number that they say is on that little module, and it could be as long as the radio is the correct model number there that they will talk to each other. So I don't know. That's why I prefer to get everything from the same place. That's why I bought my stuff from Adafruit, and I've got 3 different versions of that now. I've got the one that's the all-in-one board here that you basically plug in a USB cable and program it, and the thing you can start sending stuff back and forth. So that right there would work as a receiver. So here's the antenna on it over here, and have a USB cable. If I wanted to plug that into my laptop, or in your case, into your Raspberry Pi, that would actually work. You could just write code that says take the incoming message and send it right out the USB to your Raspberry Pi. And then I bought this one since I needed a CAN interface. I bought this one and connected it to the Teensy 3.2. And then if you want, you can buy it like this. That's the chip, and it's got level translation and a voltage regulator on that'll supposedly run on either a 5-volt processor or 3.3 volt processor. So that's the stuff that Adafruit is selling. And there's still the confusion about RFM 95 versus RFM 69. They do say right on Adafruit, those two will not talk to each other. So don't take an RFM 95 and expect it to talk to an RFM 69, because that does not work. If you got 2 of the same kind, then they'll talk to each other. And if anybody researches that enough to find out what an RFM 69 is, let us all know, so I don't have to go digging for it. And then, like you found out, you can get that ESP32 board that's got a display and one of these radios on, so that's another form factor you can go with. And then the one that Bob bought is a board that plugs onto a Raspberry Pi and has a display and the radio. So there's lots of different options on this. You just have to figure out, the fundamental thing that I found out was make sure it's got enough IO pins to hook all your stuff up on the remote control side. Or as I mentioned earlier, if you need to, you can hook up an I2C IO expander or shift registers. You can get just tons and tons of IO if you really needed to. It's just more screwing around, more chips. You have to wire up more stuff and figure out how to make it work, but it's not really all that hard.
Hey, my man, I'm gonna have to run.
Okay.
That's a lot of content for not having much to say today.
Yeah, I think so. Let me do an emergency chat save just in case. It seems to always save it no matter what, but one of these times it's not going to. That can make me mad. So did that
Saves it
work?
on my side.
What's that?
The chats anyway are saved on my side.
Okay. So, anything else?
That's enough for me.
Okay. Well, I'll click the end button then.